Thank you so much. It's great to be here. As Jesse mentioned earlier, I was here actually for the, I was one of the lecturers who was here for the summer school last week. And so today I'll be talking about a related topic that I was speaking about with the students last week, related to incorporating uncertainties into machine learning models. So the background for me is that I am an astrostatistician. So I'm between the Department of Statistical Sciences and Astronomy and Astrophysics at the University of Toronto. And so I think a lot about sort of the observation and measurement side of sort of machine learning. And how exactly do we incorporate lots of different physical processes that actually cause, noise models, censorship, uncertainties in the models themselves into sort of doing inference. So the goal here is to actually be a really, really good complement to Tessa's talk, which is focused a lot on how can we build models in such a way that we can make them robust to certain types of noise, have certain types of properties, and preserve certain types of symmetries. And this is more thinking about how do we actually propagate observational uncertainties directly into those models. So the overview here is going to be straightforward. So I focus a lot on uncertainties because they're kind of ubiquitous in all physical sciences, right? Every measurement process has some sort of uncertainty associated with them, or censorship, or both. And these will have an impact on any downstream analysis that happens. The question is how big, right? So the real thing is how much do you need to worry about that in theory or practice, right? Maybe you can design models that are very robust to certain types of noise. Or maybe you really want to propagate information into your downstream models because that's something you really care about. Are there existing methods that kind of implicitly or explicitly deal with these? I'd say yes and no. There are definitely strategies to incorporate them. And so my goal in sort of this overview is to actually give a couple examples of things from my own work and that we're thinking about in astronomy, where we've developed some strategies that hopefully will be helpful for you. And you might also have other things, and it'd be great to talk more with people about different things that people have tried. So I want to start out with just giving an overview of the types of uncertainties that we often are dealing with. I would say these fall broadly into 4 categories. Essentially, uncertainties on the inputs into most machine learning problems, and those come in the observables and the targets. So you have a machine learning model. We often sort of potentially have errors on both ends, and they affect the results in different ways. We also have errors on the model itself, and those also take 2 forms. One are the actual hyperparameters of the model, right? We often are optimizing for a particular neural network. We specified an architecture. Do we need to somehow marginalize over this, right? Over all possible models when we make a prediction, or at least, all possible parameters of a given model, if we think that we really care about that sort of level of error propagation. And also in the predictions themselves. There's not a guarantee, for example, that given some particular input X, that you're always going to get exactly one output Y, right? There's no guarantee that function is exactly bijective. And so if there's some intrinsic fundamental uncertainty in the problem, either because of information loss or something from the measurement uncertainties, we want to also be able to propagate that through to the predictions and have those interact with, for example, the measurement errors in a way that makes sense. So the motivating example I want to use for this is 3D dust mapping, because it turns out that all of these errors come in this particular problem in astronomy. I work on it. I think it's very cool. The basic idea is that we want to sort of map out the position of cosmic dust throughout the galaxy. And what we have are essentially stars. We can go out and we can observe stars, and they essentially have, different levels of brightness. So you can look at some that are brighter, that are a little fainter, and they're all over the place. And what we can do then is we're interested in using this to do a 3D reconstruction of the dust density. In other words, going from that set of observations to this. The problem, of course, is that this is not a trivial thing, because we sort of exist at some small vantage point, except that my actual pointer doesn't actually seem to be working. Hold on, just give me a second here. All right, well, guess there's no drawing. Essentially, for this particular problem, the idea is that, oh, what is happening? All right, it looks like the thing is actually completely frozen. Yeah, for some reason I can't progress. I'm like stuck on the screen.
Do you want to stop sharing?
Yeah, I'm going to try resharing quickly and see if that helps. Okay. All right, we're back. So more or less the problem is that we actually are in a weird place. So we're sort of in some particular vantage point, which is say here. And what we actually want to go do is observe sort of a given star. We don't actually see this density field directly. We see an integral of the density field. So it's a difficult constraint, and we're a particularly biased position, and all the measurements are noisy. So what does that mean in terms of what we're looking at? Well, we can make a plot like this. This shows the distance along a particular direction, an angle, and also the extinction that we observe from dust. In other words, the total amount of integrated dust along that line of sight. We get something that looks like this. And then the idea is that we'd like to fit some functional form, which should be monotonically increasing because you can't have negative dust as you sort of look out into each line of sight. And then this gets sort of, embedded in a 3D structure. So the challenge, of course, is that every part of this problem, at least from the observer side, has uncertainties. We have uncertainties in the x-axis, the y-axis. The model is very unclear, and we have no guarantee that the resolution which we can actually observe stars, there's not sort of intrinsic variability in sort of the dust that we're looking at. So what you can get from this is something that looks like this. So this is a sort of flyover, sort of taking a loop around the sun, showing sort of the 3D structure of dust in our galaxy that's reconstructed using sort of these millions of stars. So I'll display that again. All of these are reconstructed using this type of stuff, and also trying to take these observational uncertainties into account. So what exactly does this look like? I want to go through this kind of from the perspective of someone who's sort of thinking about this problem for the first time. And object one might be that we can just add in the errors, right? So normally we want to do some machine learning. We sort of say, okay, great, we have a function, and we're just going to sort of say, rather than conditioning on x, we're going to condition on x and sigma y maybe, and then we're going to predict the actual result. And you might say, well, maybe that'll work conceptually, right? It's sort of like trying to look at some particular observational uncertainty. Oh, there we go. So, in either direction. So maybe instead of just having a function that predicts y given x, you have a function that actually, predicts y given x and sigma x. And then you might say, well, and also we have some measurement error on y, and maybe we can do some type of inverse variance weighting for the a given observation, and when we train, we just don't treat that observation as well. Seems a little hacked. The question, does this work? Maybe. I'll get back to this later. But it's like a good starting point to think of it this way. So then what often comes up is you say, okay, well, maybe we can do some type of data augmentation. So Monte Carloing is great. I have some uncertainty in both of these. I can sort of Monte Carlo my results, and I'm going to integrate over it, right? We're marginalizing over it using some Monte Carlo integration, right? Does this make sense? Yes, intuitively, it makes lots of sense, and people have tried this a lot in the astronomy literature. Does it work? No. But it actually doesn't work for two different reasons, one of which kind of is obvious when you explain it, and the other one which is very subtle. So one thing it doesn't work is that you're actually double counting noise. And that's because when you train on noisy data, you kind of have already incorporated some amount of that uncertainty. So if you have some function where it goes from some input to some noisy input, x tilde here, and then you get some, but then you have some actual observation that's dependent on this y, and you're training on this noisy input to the output, you sort of have already incorporated some amount of measurement error into your prediction. And so then if you say, well, I'm going to generate some more noise by sort of Monte Carloing, you've essentially double counted. You've added your noise twice when you sort of train your model and you do that data augmentation. And you can actually show this using a bunch of examples that if you do Monte Carlo this way, it fails. The second reason is actually much more subtle, which is that when you augment the data, it seems to make a lot of sense. You're saying, well, this one object could be in all of these different positions, so I'm just going to average over all of those. But if you sort of work through the math, what you essentially have done is computed the average of some loss function, say of your true value over all possible values that you could have given some noisy input. This is sort of your theoretically what you have. Sorry, this is, yeah. So in this case, the idea is that you're marginalizing over all potential real values. You have some latent variable, and you're trying to marginalize over your loss. But this is not actually the same as often what you really care about, which is marginalizing over the actual probability, which is often the log, related to this by often being sort of related to the loss is the log probability with respect to those same things. So what this essentially means is that when you do sort of data augmentation, you're essentially taking an average in log space, you're taking a geometric mean. But what you actually want to do is to average in probability space, which is taking an arithmetic mean. Essentially, the average of the log is not the log of the average. And so when you do data augmentation using this type of strategy, and this is true for any generic measurement error or process, you have to be careful when you're sort of simulating new data to make sure that you're not marginalizing in this way. So double counting is the most obvious one, but this other one is much more subtle. Okay, so the solution to this is that we need to write down a model, right? We need to write down some probabilistic model that actually generates our observations, given sort of, some noise properties and other types of things, and we can turn that into a loss function. Once we can write down sort of a final joint probability over everything, we can then work through the math, marginalize over our noise model, and that's ultimately what we will then turn into our loss function. And you can imagine now using something where you can take your model, you might even make it probabilistic, right? You might even add some additional uncertainties into that model, and we can now sort of take into account the fact that when you have some observed uncertainty, really conceptually what you're trying to do is compute this overlap integral between your errors and the model. And that's ultimately what your loss is going to look like, is where those two things overlap. So when you adjust things up or down, you are sensitive to all parts of your error distribution. This works in general, so you can have very, very complex error models. As long as you can compute this sort of overlap region, you're fine. So does this make sense? Yes. Does it work? Also yes. And in fact, one thing I just want to show is that you can actually implement this type of custom loss function, and you can do proper sort of Monte Carloing within something like TensorFlow. So you can actually take all of those same sort of Monte Carlo simulations, and you can compute this overlap integral. The thing is, you just have to make sure you do it before you take a log. So when you put it all together, you get something like this. This is some code written by a summer student I was working with, Ava. And this just shows essentially how you would implement this. It also includes an outlier model, which I'll get to a bit later. And then the nice result is that you get something that looks like this. This is, again, the same problem where you've simulated a bunch of data, essentially from in a box. This is using a baseline model where we've completely ignored the errors or tried to do augmentation, and we get the wrong answer, which is shown in green, compared to the underlying, which is in gray. And if we actually do a full probabilistic model where we take everything into account, you can't even see the purple curve for most of them because they just agree so well. So it really does work in theory and in practice. All right. The last thing is you might say, okay, this is great, but you also talked about potential predictive uncertainties and how would I extend this? One really popular tool that people use now is essentially this type of simulation-based inference, or really that's just conditional normalizing flows, which goes from predicting a particular function, f of x, to essentially trying to predict, p of y given x in most cases. Or in our case, if you have noisy data, we're sort of trying to predict, p of noisy y given p of noisy x is really how we want to phrase the problem. And you can also modify this in the same way. And indeed, when you ask if it works, you have to do a little bit of maneuvering, but yes, it sort of works in the same way. You could do the same type of integral. And in fact, one more set of recent work that we've done has been extending it to even more complex noise models, including heteroscedastic noise and censorship. So here's a link to a paper where we did that. The technical details I'm happy to talk about with people afterwards. But more or less, the big takeaway for this is just be really careful when you Monte Carlo. This sort of example shows if you do things right, you write down some custom loss functions. You can work with very complex data. It all works fine. But if you sort of take a naive approach, you need to be very careful. The other way that I've been thinking a lot about this, and other people often talk about it, is in the unsupervised regime. So in this case, we're talking about some explicit set of targets. But if we're trying to just find structure or doing clustering, we also care about error propagation as well. And the way I want to motivate this is in astronomy is through something called chemical tagging. So stars are born essentially from the same cloud of gas, and that means they often have the same set of chemical abundances. But over time, those stars kind of disperse across the galaxy, and that means if we can sort of identify the particular chemical fingerprint, we can figure out how and when stars were born. And one way to look at this is by going out and actually getting a star cluster. So this is a bunch of stars that are actually on the sky. So this is in essentially right ascension declination. And this is selected through a survey called Apogee, which is through SDSS. This central region here is sort of a star cluster we've identified. This red area is something we're interested in searching. And so what we can do is we can go and look at essentially a bunch of different chemical abundances that have been measured from spectra. This top panel essentially shows the results from this cluster center. The bottom shows the results from the background field. And the main takeaway, rather than looking at anything in particular, is that these two things are very different from each other. So this particular star cluster looks very different from the background set of stars, which have all sort of dissolved and migrated throughout the galaxy. And this unique chemical signature shows up if we want to do, for example, dimensionality reduction, because clustering in high-dimensional spaces due to the curse of dimensionality is very inefficient, and because many of these abundances are actually very correlated. So there's really sort of a fundamental basis for many clusters in terms of what makes their chemical signatures unique. So if we do that using, for example, off-the-shelf algorithms like T-SNE or UMAP, you get something that looks like this. This is our 19-dimensional space projected into a 2-dimensional space. And we've identified all the stars that we selected spatially in that clump. Turn out they're all right there. So they do look essentially chemically distinct from lots of other stars in the region. But we've also ignored a very important thing, which is what should we do about the errors? And this was a project that originally was started by a graduate student at Toronto, Stephanie Grandin. And we've since sort of expanded this to try and answer this general question of how do we do essentially error propagation through probabilistic embeddings, right? You want to do dimensionality reduction. You want to keep error bars in there somewhere. How exactly do we do this? So one thing I can tell you is you might say, well, maybe Monte Carloing works here. And the answer is also it's terrible. You absolutely double count the noise. This is a projection now using UMAP, same data. So you can see sort of most of the cluster exists in this particular region. If you then sort of keep the same projection, you Monte Carlo a bunch of noise onto that projection and do augmentation, you get this, which is a mess. But the main thing to look at is essentially that this original, very well-defined cluster sort of has scattered off into all of the regions into the background. I apologize for the color choice. The red and green was from the student. So, of course, I would never make such a default color scheme plot. No, it's in this case, what we find is that we get a decrease in sort of the accuracy from about 97% to 60-something%. And again, that's because we're double counting the errors. So this also holds true if you just look at field stars as well. They sort of scatter across this surface in a very non-Gaussian way, even though the input errors are all Gaussian. So we had a question, which was, could we develop some methods to try and deal with this? And we started with these variational autoencoders as a really good baseline. The reason for this is because they essentially allow us to do some form of incorporating a custom loss, which is what we sort of are interested in for doing marginalization over noise. By taking sort of our input data, projecting it through essentially an encoder and decoder structure, and having sort of this latent space in the middle. And ultimately, how it trains is by looking at this reconstruction loss, essentially the difference between your output decoded result compared to your input result. And this gives us a lot of room to play with, both in terms of modifying the architecture components here, the possible latent space, and the loss function between both of these. And so we take a strategy that attacks both problems at once. One thing we did was we tried to develop what we call a scatter VAE. This was work that was led by PhD student Alex LaRoche. So mainly for this plot, I want to focus on this bottom part here. The top part just shows the actual observed data we're looking at, which is taken from the Gaia survey, which is a large astronomical survey of about 2 billion sources. And all that we've sort of done here is that we've modified essentially our loss function to incorporate errors in a very natural way. And we've also added in estimates of the intrinsic uncertainties into this problem. So using both of those tools that I mentioned before, right? Custom loss functions that develop from a probabilistic model, and also trying to input intrinsic uncertainties into this network due to, potential input errors. The second thing we did is we developed what was called a distribution VAE. And this one, we actually had sort of a bifurcated double encoder structure, where we essentially put in both the measurement and the error and have them proceed on these parallel tracks through our model, where sometimes the measurement is able to impact the error, but the error never impacts the measurement. And that's just one way of saying that we allow for nonlinear variation in how our errors behave. But the idea here is that if you start out with a normal distribution in your high dimensional space, we want to find a latent target that also has a normal distribution. So we go from 19-dimensional multivariate Gaussian to a 2-dimensional multivariate Gaussian. And we want to force the model to learn so that that is true by construction. So we call this a distribution because rather than trying to think about some custom losses or things like that, we're really trying to preserve this probabilistic structure throughout the network, right? Rather than going from essentially some observed data to a point and thinking about it in a specific way, we're really thinking about how do we pass distributions through our entire network from end to end, right? So not necessarily like just the normalizing flow, but if we actually really did have probabilities go through all the way. The performance comparison is pretty stark. So these are the set of results we get when we use essentially out-of-the-box methods. So these first two are UMAP and TSNE, these sort of really standard dimensionality reduction approaches. This last one is variational autoencoder. We're plotting essentially the residual for the most common, or at least the highest single noise abundance, in this case, iron. So what you can just see is that the typical measurement error that we have is pretty small. And most of these algorithms are essentially not able to reproduce the data to the same extent, using essentially 2 dimensions. And we might think that this is something intrinsic about the actual complexity of stars. What we show is that once you actually include sort of these additional components, in fact, we can do quite well with just 2 numbers. And both of these models actually do about equivalently well. And the distribution VAE is in fact able to reconstruct the uncertainties to very, very high precision. So we really are able to encode this type of structure. And again, this is something where you originally, if you're looking at the noisy data, you might think, oh, the problem's more complicated. I need sort of a more complex latent distribution. But by dealing with the errors in a more rigorous way, we show that actually you can do much better with exactly the same data just by taking the errors into account. So there really is some true error deconvolution that's happening here that the network is able to learn from the measurements. The latent space also has some fun changes, so I'll just show the plot. This is essentially the default version of UMAP, now run over about 300,000 objects. And this is the equivalent one after we train our autoencoder. And you can see that the color bar here, which is essentially the measurement of this metallicity, the residuals from before, become much smoother, and the main general structure of the space is preserved. So overall, you get some nice quantitative and qualitative differences when trying to imagining doing clustering analysis, which is sort of our next step for this type of project. Okay, the last thing I want to mention quickly is also thinking about how we can incorporate uncertainties and robustness more broadly into these machine learning frameworks. So not just directly into the model themselves, but how do we think about embedding that model into a broader inference framework so that we can deal with uncertainties both within the model and outside of the model. So one way that I like to think about this is that I'm very paranoid and I'm always concerned that I'm going to get some super weird data that's going to come in and my model's going to generate a prediction. I'm going to have no idea what happened. And so my general feeling is that the model should probably try and do its best to handle it if it's not too weird. If it's really weird, your model should throw up a panic button and say, whoa, what are you feeding me? Please stop. I didn't want vegetables today. Or decide to transition between the 2 options in a principled way. And so, in other words, I really think, and I want to encourage all of you to really design models and test your models with outliers. Try and implement as part of your normal testing frameworks, putting in out of distribution data and just seeing what happens. Right? Because it's almost certainly going to happen when you deploy it in practice. And so you want to at least understand what those failure modes are. In general, the main thing that you can conclude from this is that a mediocre model is much better than no model. And that's just true for all types of outlier detection. So you can put in something really bad that is not all a good fit for your data, but it's still better than having no model at all because a single outlier can dramatically impact how your model trains. You might not be aware of it. These can be difficult to spot. There are a lot of options for doing this. You can use inflated tails, for example. You don't need to assume Gaussians. You can use student T's. You can use mixture modeling, which is what I'm going to show in an example, like Gaussian mixture models or something else. You can use probability checks. You can train, say, density estimators and say, essentially, if you're below some threshold in your training distribution, please don't predict at the edges. So that way you're not sort of extending out of the train distribution just in terms of the inputs. You can also do things like manifold distances. If you want to find essentially some local subspace that you think is a good characterization of your data, you find the normal vector and you sort of try and measure how far that you can get from that distance. There are a lot of different options. They all have different pros and cons. In practice, you can look at this in a couple different ways. The example I want to give is through something called gyrochronology. And the main thing here is that we're trying to essentially determine the ages of stars based on how much they slow down over time. So stars sort of lose mass, and thanks to magnetic activity, that mass gets dragged really far away from the star. And that means that over time, stars start spinning really quickly and then slow down. This is a plot showing essentially the distribution of periods and masses for a whole slew of clusters, with ages starting from essentially the top is the youngest, and then the bottom over here is the oldest. And what you can see is that this has very complex structure. You get essentially bimodal distributions, essentially what's called the fast and the slow rotator sequence kind of evolve over time and show up consistently. There's mass-dependent evolution. And the main thing is that there's lots of observational effects because different clusters have different numbers of stars, different effects in terms of how well we're able to observe them. And these types of issues in the observations also can come up when training, right? If you have very essentially heterogeneous data selected and gathered very different ways, it can be very difficult to accommodate all of those different effects when you train your model. That's why a lot of people find it so important to use a homogeneous data set. So what are we going to do here? We want to essentially model this distribution empirically. And the first thing we do is we actually write down a custom loss function, which includes outliers as part of the model. And we define it in such a way so that we're predicting essentially these conditional distributions. So here's the data we have, which is a very different type of problem than I think in most of machine learning. We have a lot of data points, but they're concentrated at particular slices of the distribution. So essentially, we have a bunch of stars at a fixed age, a bunch of stars at another fixed age, and nothing in between. And we just hope that when we interpolate between sort of those two regions from these different star clusters, that we do okay. When we train and we do predictions, we find that we do. And part of this is because we went through a lot of work to make sure that the way that we trained the model and the types of losses we were looking at were robust and made sense. In particular, robust to outliers because we cannot select cleanly stars that we're confident are at a fixed age. So we're confident that like 95% of these stars are probably correct, but there's 5% contamination. We want to make sure that that doesn't destroy our model. The second thing is that we put it into a larger scale framework as well. So this is sort of showing what we did. We decided that to avoid selection effects, we'd actually condition our model on both sets of input parameters, which is not an intuitive way to solve this problem. But what it allows us to do is essentially put this in the context of a full Bayesian inference model, where we can actually specify two different types of priors on this distribution. And these priors actually allow us to put in, for example, results from theory. This prior is actually based on theoretical stellar models that we can sort of put in, and that allows us to tune how sensitive we are to essentially various things. This prior essentially describes the distribution of ages throughout the galaxy. And so we can actually tune that depending on the specific application without requiring us to retrain our machine learning model every time we want to move to a slightly different domain. So we're using one domain, and because we framed it this way, we can extend it to other domains and also deal with these out of distribution results. These all get combined into one particular model down here. And we even have an inference framework to infer the total age of the entire cluster along with a particular pipeline to make sure that that estimate is reasonable. So the idea is that we have one machine learning model, which has a particular basis. We want to train it to be robust to outliers. And by putting it in the context of a larger statistical framework where you have lots of different pieces that allow you to put your thumb on the scale, you can essentially use that to your advantage to essentially have more points to sort of check for issues with outliers or robustness, and also more places to kind of put in more informed results on errors. We also do this in testing because we only have 7 clusters. And usually when people talk about machine learning, we don't talk about 7 data points, unless, of course, we're talking about equivariant neural networks. We're trying to expand this to 16. And so we actually do validate this by brute force retraining our model by removing one cluster at a time, which proves that we actually do really well. So we are actually able to reproduce most of these ages. We find that we get an exact one-to-one relation with roughly a scatter of about 0.1 dex, so issue a sort of like, 10-ish%. Okay, so the general takeaways for this hopefully is a very different style talk than Tess's. But the main idea is to try and give you some examples of how to take different strategies and put them in practice. The first takeaway is that the best model that you can have for dealing with errors is a probabilistic one. Like if you can derive your model from an actual graph, you know what your probability distributions are, you have some estimates for where approximations come in, that allows you to define your custom loss function. And as soon as you know your noise model, you are locked into a particular loss function. That's one thing I want to emphasize. When you don't know your noise model, you can choose different loss functions, but as soon as you do, there is one preferred loss function that should be correct. And that's something that you can always aim for and hopefully derive. Monte Carloing is dangerous, but it does work fine if you define the right model and use the right math. So if you apply this naively, you get, you're very at risk of double counting errors, which actually degrades your performance artificially. And if you are trying this, you might not even need to if you can just directly propagate these distributions through your model by slightly modifying your network architecture. If you have normal distributions, you just need to keep track of 2 variables instead of 1, for example. If you have higher order distributions, you can always do essentially some moment generating functions. There are lots of ways to sort of try and propagate this information into your network. Simulation-based inference is a really appealing option to bypass some of these issues, especially issues related to model predictive uncertainty. And finally, I think that it's good to at least know that models should be designed and tested with outliers in mind, and that can also go into how you deal with your loss functions too. So hopefully that's plenty of time for questions, but that's all I got.
While I walk around, that seems like a very dangerous asterisk next to that sum. Can you
Oh, you want to explain the asterisk?
I would like you to explain it since I'm a simulation-based inference person. Like, what do I need to worry about?
Right. So the main thing is that simulation-based inference is very good if you can condition on the right things. But depending on how complex your noise model is, or whether you can even actually model it directly, sometimes that can be very difficult to do. So one of the things that we've tried, for example, in astronomy is that in theory, you can just condition on your observations, your error bars, that should be enough. But because the error models can be so complex, if you try and actually span the entire space, your performance actually degrades substantially, and it becomes much harder to train those models just because you've doubled or tripled your parameter space. And so you can use other tricks to sort of deal with censorship, to deal with heteroscedastic errors, and that helps. The other thing is that depending on exactly what types of uncertainties you're really worried about, simulation-based inference doesn't really capture them. So if you're worried about essentially fundamental model uncertainties or marginalizing over all possible sets of models, SBI doesn't really capture those. But it is great if you are trying to deal with predictive uncertainties, I think, and that is a huge benefit.
Right. So you showed a lot of plots in 2 dimensions effectively for latent dimensions.
Yes.
And so my question is about, asking you about commenting why 2, and like, is there because it comes at a price, right?
Of course.
And yeah, should we be exploring higher dimensions, or what are your takes? What are your thoughts?
So I think, one, so I showed mostly 2 because those are easy to plot.
Yeah,
that's always the trick.
That's not to do
but I think one of the things that we discovered going through these projects is that in the past in literature, people have kind of, explored various dimensional sizes, try and visualize them. And what we found essentially is that some of those results might have essentially been due to the fact that they weren't accounting for observational uncertainties when they were doing this reduction. Like you actually do seem to find a much more condensed subspace when you do that. I don't think you need to always stick to 2. I think, N is the, you should find the N that sort of maximizes your, interpretability versus science results, et cetera. But the general properties that we derived in terms of having some N-dimensional embedding, which has, some guaranteed error properties, that does appear to be general. Hopefully that roughly gets your question.
Just to stick a bit more, right? So what would be like on the cases that you've shown on stars effectively, why should it be 2 there?
So physically, we know that it has to be at least 2, because sort of the main driving processes for stellar evolution and galactic dynamics is often driven by metallicity and also by essentially alpha process elements. So we know that it's a minimum of 2. The argument is often how much more than 2 is it? Are we really looking at additional abundance properties that can affect stellar evolution to a large extent, or are we really just looking at small cosmetic changes that don't really change the stars that much? And, arguments in literature have ranged anywhere from sort of, 2 to 6 to 15. And, so they've gone back and forth. So we're hoping to sort of figure out what's the sort of correct fundamental basis there.
Thanks for the nice talk. So I have a question about you're mentioning about the Monte Carlo method. So of course, the Monte Carlo method have some dangers about the double counting errors. But have you also considered the bias correction methods? So for example, you can just consider the prediction based on the smeared data set and the doubly smeared data set. And if you can use the differences of the predictions to correct these double counting errors. Have you also considered that directions?
Yes, so we have looked into this. You can always try and do some error bias correction to account for this. So, I mean, yes, this is generally a pretty decent approach. But my general take is like, if you don't need to do that, then you can just do it directly, right? Like, if you don't need to Monte Carlo to, if Monte Carlo is, if we know it's wrong, but we might be able to bias correct it because it's doing half of something right, we might as well just do the correct thing instead. But yes, we have actually, there is a paper where we do sort of this double counting method because that's what we want to do to sort of get uncertainties out. And then we also then apply sort of a bias correction method to sort of adjust all of the results for the expected bias that comes in, and then also adjust the errors, which we find are all overinflated. So it does kind of work. It's not perfect. I don't want to go into lots of discussion about like coverage guarantees that come from this, but essentially you become penalized because you've started doing something wrong and you're really just trying to correct it to something that's a little better.
So the message is then if we could play with the distribution directly, then it's better to play with it directly.
Yes, so I think the bias correction approaches are great if you can't essentially sort of write all the stuff down directly, but if you can, that's always the preferred option. So, and that can be either through something like the loss function, if you know that you can write down a probabilistic model, or it can be through the architecture, right? If you want to define something that's equivariant or something that respects lots of symmetries or behaves in a certain way, you can just put that in rather than having to deal with, adding in custom loss terms to sort of try and prevent, different types of rotational invariances or whatever. Yeah.
Thank you so much.
Hi. So you had this slide where you had these two like kind of tracks, one for the main value and one for the error value.
Yes.
And you project down into this latent space, and you said you enforce that the errors are Gaussian in the latent space, but I don't understand why there would be Gaussian. I mean, if it's just any function coming in, I mean, say you start with a Gaussian and then you just take the log, then it's no longer Gaussian. So why would the latent space error be Gaussian? I don't understand that.
So in this case, for that parallel track one, well, I think it's a couple slides back, but for the parallel track one, we enforce actually that Gaussianity. There's no reason to, it's just it makes the error properties well behaved. So normally for variational autoencoders, there's sort of this two-part loss. You have kind of what I call the reconstruction loss, and then you have a structure loss, where you have some KL divergence between essentially your projected distribution and then some normal distribution. And all that we've done is we essentially have said that we've modified that term so that now, rather than just trying to compare to something that is 0, 1 with some arbitrary mean and variance, we actually are putting in a prediction for what we expect those errors should be based on the observations, and so by construction there, we sort of have enforced it to be Gaussian. But there's no, in practice, there's no reason it has to be. And you're right that if we were doing any sort of dimensionality reduction, we take a Gaussian, we transform it arbitrarily, the errors wouldn't be Gaussian. So we're trying to solve a slightly different problem of finding not just any latent space, but a specific latent space for which the projection of some of the high dimensional errors to the low dimensional space also retains its Gaussian properties.
Okay, thanks.
Mm-hmm.
I was hoping you could comment a little bit more about the case where you can't drive a probabilistic model, in the sense that maybe you don't understand your underlying parameters very well, or you have some phenomenological model of them, but you don't think it's very accurate. Like, I know we talked a little bit before in some of the other questions about that, but kind of what else can you do in that case?
Right. So you can come up with some workarounds. So in some applications that I've looked at where essentially the actual underlying model is too complicated, but you can get samples from the model, you can still use some of this kind of Monte Carlo integration strategy to at least marginalize over that noise model, even though the actual underlying distribution is unknown. That helps, but you can also have cases where you don't even have that. So you just have some set of observations, the noise model is complicated, maybe it follows certain forms, but you can't actually derive it directly. In those cases, I think the best strategies are really trying to see sort of under different assumptions how much your model changes and how sensitive it is to those. So in that case, you're not locked into a particular loss function, but different assumptions, for example, between mean square error, mean absolute error, all these different things correspond to different assumptions about the noise properties of your distribution. And you can imagine constructing a functional form that allows you to play with the overall tails of, say, a student T, or adding in, potential outlier components and seeing how much it affects the downstream inference once you marginalize over those properties. So I don't think there's a good answer, essentially, in that case. That's a very hard problem if you don't have enough information to make some headway into a noise model.
The questions for Josh. I have one last question on my side. So your orange statement here, the best model is a probabilistic one you can derive. Great, I'm all behind that. Can you just say again, in the first part of your talk, you talked about things in the supervised case. In the second part of your talk, you talk about things in the unsupervised case.
Right.
I think in both cases, you would say the same orange sentence.
Yes,
Can you just say
absolutely.
a little bit more about the differences between those cases? When I don't have a target output, how does that affect the way that I think about uncertainties? Naively, it just seems like it becomes a much easier problem, that somehow unsupervised is even easier to think about. But is that the right way of thinking about it, or is there some other way I should think about that distinction between supervised and unsupervised uncertainties?
Yeah, that's a great question. So I think it depends on what's going on in both cases. So in the supervised case, I think it's direct. You're sort of saying, okay, I have some error model, I need to marginalize over these particular variables. You sort of go through the process and then you end up with some target distribution. Maybe that target distribution of errors you have to marginalize over too. In the unsupervised case, things are somewhat easier because you only have one class of uncertainties to consider. So that helps. But in cases, say, where you're doing dimensionality reduction or you're trying to implement, say, flows, then the question is you actually are doing something slightly different. So if you're doing dimensionality reduction, you've introduced a second set of variables for which you might want to be able to model errors or have certain properties. And then in those cases, you still have to make sure that the assumptions that you made sort of in a naive model still hold up in that particular model. So in the example with the variational autoencoder, we sort of showed that if you ignore the uncertainties or you put them in a naive way, you don't really get much improved performance. It's only when you sort of are able to modify different parts of this model where you're really able to get that benefit. But I agree that it is easier in the unsupervised case because you don't have to worry about this essentially asymmetric loss that comes in when doing a prediction. You really just have to worry about the loss on sort of just your observables.
Great. Any last takers before the break? Okay, if not, thanks, Josh.